Yeah.
How do you change to the?
Just.
Oh yeah, cool. Got it. Right, thanks a lot.
That's not that. Maybe the pen, right? Oh.
Interesting. It doesn't have the license for it.
Yeah, I do actually. Let's try. All these minor things. Let me see if I can fix it.
Should
Now,
we try stop share?
no, it's fine. Doesn't matter. Doesn't matter. I will put the license code in, and I will also. We could stop sharing the screen, couldn't we? So I'm Trello. I've got to do it from here. How you doing, Alan?
I'm alright.
You alright? Enjoying your holidays? You working hard?
Actually, you can't get into the habit of waking up early, so in the holidays you can just get up at the same time.
And do loads and loads of work, yeah?
Yeah, where are the lights for?
Just there actually. Right. Enter license number. And I'll try. What computer is this? Number 2. Should I try the first code or the second code? One, 0, 1. All right.
My dad was like this.
Second one is used. Here's the first one. Default reader. Now we've got a formatted paper. Just where is it?
Does it matter? Can we not just?
No, it does matter because look, you got no space. What?
Yeah, this is gonna be here for like ages.
Hmm. Okay.
We could work on a blank piece of paper.
You could work on a blank piece of paper. Yeah, you're completely right. But let's just see if we can do it, shall we? Let's just see if we can do it anyway. Actually, yeah, add a link.
No one's signed into pages.
There you go. Faculty downloads, ZNotes. You don't need to sign the Slack, really, do we? ZNotes.org/A2 coach. This would be a link in the Slack, but it's probably easier to just type the link straight in. I'll go to. Yeah, okay, thanks for that. Maths 709. I said no. Paper 52. That's the one. And we'll do the stats one. You can do the stats one.
Afterwards, yeah.
Yeah, brilliant. Perfect. So I'll download that. Oh. It's a shame that the stats page wasn't found. Oh well, you might have to do the stats a different way. Yeah?
Yeah, that's good.
Better than that. Okay, now I just need to go back and share the screen again.
Great, thanks.
That's yours. Yeah, well, that's going to take a composite.
Yeah. Um, well, now we started. But is the mic working?
You might not have pressed one.
We have no idea how to use it. Oh yeah, it is.
Oh, okay.
It's working.
Okay.
Okay, cool.
Okay, so cool.
Yeah, finally. So this is the June paper from 2015 for mechanics. And let's look at question 1. A particle of mass 0.6 kilogram is on a rough horizontal surface. So let's call this O and P. And particle P has mass 0.6 kilogram. And the distance OP is 0.4 meters. And the disk and P rotate with angular speed 3 rad per second about a vertical axis which passes through O. Find the magnitude of the frictional force which the disk exerts on the particle and state the direction of this force. So it's basically a circular motion problem. And we know that for circular motion, F is equal to ma and is equal to v squared over r, and it's also equal to omega squared r. And have you done any calculus before? So because this formula is so much taken for granted, we can first look at how to derive this formula from first principles. Let's think about how we can represent the position of the particle with parameter theta and the radius r. So at any given theta on this circle, the coordinate would be r cos theta and r sine theta, right? And we know it's a two-dimensional motion because it always is with a centripetal force. So basically, whenever you have a centripetal attraction force, the motion can always be reduced to a two-dimensional case. And here, we have a representation of the position of the particle. This is the position, we call it by x, underline x. And now, how do we calculate v from x? We do the obvious step. We differentiate. So we get r minus r sine theta, and use chain rule here, d theta by dt. And we differentiate r sine theta to get the same thing, r cos theta d theta by dt, where we have used the fact that r is just a constant, and the only thing that's changing with respect to time is theta. And in order to work out the acceleration, we further assume that the rate of change of theta, which we just call omega equals to d theta by dt, we assume that's constant. So when we differentiate this expression again, we don't need to differentiate d theta by dt because that's just a constant. We only need to differentiate sine theta again. So we get minus r cos theta d theta by dt squared, and r minus r sine theta d theta by dt squared. And it gives you two very important detail. The first one is that A is proportional to minus x, which means the force is acting towards the center. That agrees with our previous intuition. And the second thing is that the magnitude of A is the same as m omega square r, which you can just observe by noting that the difference between this expression and this expression is just omega squared. And this is where we get the formula from first principle. And whenever you are confused, you can always start from this starting point. And this is the same with a lot of mechanical problem, where if you just start with position and proceed by differentiation, you can get V and A from X easily, and you'll never go wrong by this method. And while this question is pretty much trivial, if you just use this formula, we get that F is equal to 0.6, which is the mass of the particle, times 3 squared, which is the angular velocity of the particle, and times r, which is 0.4. So this is m this is omega squared, and this is r, and that just gives you 2.16. And where is the force pointing towards? Well, we know that in circular motion, in the lab frame, which the center is the center of the motion is stationary, the force is always centripetal, which means it's pointing towards the center of the motion. So it's basically the force is radial and pointing from P to O. Any questions about? Okay, cool. So question 2. One end of a light elastic string of natural length 0.5 meter and modulus of elasticity 30 Newton is attached to a fixed point O. So let's draw a diagram here. So a fixed point O and a elastic string of natural length 0.5 and the modulus of elasticity 30 Newton. And we have a mass P by the end of the string. And so we have extension is 0.3 meters. And for this question, we just need to use the formula. We are asked to find the mass is 1.8 kilogram. So in equilibrium, all the forces should balance. So mg will be equal to 30 times 0.3 over 0.5. And the formula to remember here is that elastic force is equal to extension over the original length multiplied by the modulus of elasticity lambda. And after this calculation, we'll find out that m is equal to 1.8 kilogram as required. For the second part of the question, the particle is pulled vertically downwards and released from rest from the point where OP is equal to 1.2 meter. So OP 0.5, and the extension here is just 1.2 minus 0.5 will give you 0.7. And for this question, it's not very helpful to consider force. It's more helpful and easy to consider energy. So let's consider the elastic energy stored, elastic potential energy stored in the string. It has the formula EE is equal to the modulus of elasticity times the extension squared, extension squared over 2, and the original length. And we put in the numbers with 30 times 0.7 squared over 2 times 0.5. And after you work out the this energy, we use the principle of energy conservation. We say that the kinetic energy gained by the particle at that point will be 1.8 v squared over 2. And that should be equal to the gained elastic energy minus the gain in the loss in gravitational potential energy, which is equal to 1.8 times 1.2 minus 0.5 g. And after rearrangement, you get v is equal to 1.53 meter per second. And yeah, the thing to remember here is that you have different kinds of energy converting into one another. So in the beginning, you have equilibrium where all the forces balance, but then a force is applied, so work is done to bring the particle to a new position, and elastic energy is stored in the particle. And then when the particle is released, it will be moving upwards, gaining gravitational potential energy and kinetic energy. And because we know the value of elastic energy stored in the string, we know the value of gravitational potential energy gained in the motion, we can simply do Ke is equal to elastic energy minus gravitational potential energy. Question 3. So a triangular frame ABC consists of 2 uniform rods, each of length 0.8 meter and weight 3 Newton, and the longer uniform rod of weight 4 Newton. So it should be something like this. And the 2 shorter rods will be 0.8 meter each. And we are told that this angle is equal to 30 degrees. And by some very simple trigonometry, we will get that this is 0.4. And now we are asked to calculate the distance of the center of mass of the frame from AC. Well, you can consider the center of mass as a weight average of the individual center of mass, or you can use the fact that in equilibrium everything should balance, and in the sense that the whole forces on each individual rod would add up to a single force through the center of mass. So let's draw another diagram. Let's call the center of mass O, and this is the weight of all 3 rods. And by the fact that it's the center of mass, we take moment about this line AC. So we call the distance between O to AC D. And D times the total weight of the object, 3 plus 3 plus 4, should be the same as the total moment by treating each rod individually. So here we'll have 3 Newton times 0.4 sine 30 times 2, where we're summing the 2 individual moments here. And that will give you D is equal to 0.12 meter. Okay. And now the vertex A of the frame is attached to a smooth hinge at a fixed point. The frame is held in equilibrium with AC vertical by a vertical force of magnitude Fn applied to the frame at B. And we're asked to calculate F and state the magnitude and direction of the force acting on the frame at the hinge. Well, if we want the force acting at the hinge, we need to resolve forces. And we know that the weight of the entire frame is equal to 3 plus 3 plus 4 is 10. And they are all acting through the center of mass, which is at the distance 0.12 meter from the line AC. And from these 2 conditions, we can take moments about A. So what do moments represent? To represent the turning effects of each individual forces. And for a object in equilibrium, there should be no turning. So the moments about any single point on the plane should all sum to 0. And when we take moments about A, we find that 0.12, the distance of the weight, times 10 should be equal. So this is the moment of weight should be equal to F times 0.8 times sine 30. And this is the moment of F. And they should be equal to magnitude because they are different in direction. The weight is trying to turn the object clockwise around A, and F is trying to turn this object anti-clockwise around A. And finish this calculation, we get F is equal to 3. So if F is equal to 3, and we resolve forces vertically, we find that 3 plus the forces acting at A, let's call it Fa, must balance gravity. So Fa is equal to 7 and acting vertically upwards. We can see there's no horizontal force because there are no horizontal force at B or C, therefore there's no horizontal component of Fa. Question 4. So one end of a light inextensible string of length 0.5 meter is attached to a fixed point A. The other end of the string is attached to a particle P of weight 6 Newton. Another light inextensible string of length 0.5 meter connects P to a fixed point B, which is 0.8 meter below A. So by some really simple Pythagorean calculation, you'll find that the radius of this circular motion is 0.3 meter. And we're asked to find that when the tension in the string BP is 2 Newton, calculate the speed of P. Well, if the tension in BP is 2 Newton, in order to balance the weight of P and the tension in AP, we can do a resolving of forces. So 0.4 over 0.5, that's basically the cosine of this angle, theta, times the tension T in the string AP minus 2 times 0.4 over 0.5, which is effectively the cosine of this angle, which is also theta. And that should give you the weight, because you have tension here pulling upwards and tension here pulling downwards, and you have weight here going downwards. So if we resolve vertically, this must be the case. And we can calculate T to be 9.5 Newton. And now we can apply Newton's second law horizontally, so that 0.5 Newton is the tension in the top string times 0.3 over 0.5 plus 2, which is the tension in the bottom string, times 0.3 over 0.5 must be equal to 6 over g, which is the mass of the particle, times v squared over 0.3, which is the acceleration of the particle. So this is basically a statement that F is equal to ma. And then from this expression, we can get that v should be 1.86 meter per second. And in the second part of the question, we're asked to show that the angular speed of P must exceed 5 radians per second. And for this kind of string questions, an upper or lower bound on the speed is almost always related to when the string becomes slack. And because here we have the condition here, so we have to ensure that the strings never become slack. So we have the condition that 0.4 over 0.5 T is equal to 6. This is at the point just before the string at the bottom becomes slack. So basically, the tension in the top string just balances the weight of the particle. And from this calculation, we get that the tension in the top string is 7.5 Newton. And given this this condition and the fact that there's no tension in the bottom string, we have Newton's second law here. 7.5 times 0.3 over 0.5 is basically the only centripetal force given to the particle, is equal to 6 over g, the mass of the particle, times omega squared, the angular velocity squared, times 0.3, the radius. And that will give you omega is equal to 5 radius per second. And what happens when the velocity is less than 5 radians per second? Well, then the radius must get smaller, and in that case, BP will not be in tension anymore. Question 5. Well, let's call the point at the bottom P. A uniform solid cube with edges of length 0.4 meter rests in equilibrium on a rough plane, inclined at an angle of 30 degrees to the horizontal. And ABCD is a cross-section through the center of mass of the cube, with AB along a line of greatest slope. B lies below the level of A. One end of a light elastic string with modulus of elasticity 12 Newton and natural length 0.4. So the modulus of elasticity is 12 Newton. The natural length is 0.4 meter. Is attached to C. The other end of the string is attached to a point below the level of B on the same line of greatest slope, such that the string makes an angle 30 degrees with the plane. The cube is on the point of toppling. Find the tension in the string. Well, if it's on the point of toppling, let's just first calculate CP. And CP should be, by using trigonometry, 0.8. It's basically just 0.4 over sine 30 give you 0.8. And we know its current length, we know its original length, and we know the modulus of elasticity. And it's easy to calculate the tension. And let's just do it again. It's equal to lambda times the extension over the original length. It'll give you 12 in this case, times 0.8 minus 0.4 over 0.4, and that will give you the tension being 12 Newton in the string. And now we're asked to find the weight of the cube, and let's just concentrate on this diagram first. Because it's a uniform solid cube, we can argue by symmetry that the center of mass is obviously in the center of the square. So we have a weight. What's the weight of the? Oh yeah, okay. So let's call the weight W. And we can take moments around B. And there are two components of W, and this is what's going to be tricky here. There's one component that's perpendicular to the plane, and another component that's parallel to the plane. And the sign of the moments of these two forces must be different, because this one acting perpendicular to the plane, let's call it force 1. It's going to try to turn the cube in a clockwise fashion, but the second moment on the top is going to try to turn the cube in a anti-clockwise direction. And it's quite obvious that the tension is trying to turn the cube in a anti-clockwise fashion as well. And we can ignore friction if we take moments about B, because friction is going to act along this slope and it's going to pass through B. And whenever we're taking moments about a point, say B, and a force passed through that point, its moments must be 0, because there's no distance between the force and the point of interest. So now we have all the information we know. So take moments about B. So we have 0.4 times 12 cos 30. And this is the moment of the tension. And we worked out its magnitude is 12. And cos 30 is the cos of this angle. And so 0.8 times cos 30 gives you this length. Is equal to 0.2 W cos 30 minus 0.2 W sine 30. So these are the two different components of gravity. And it's just a linear equation now, which can be solved to give you W is equal to 56.8 Newton. I guess a point where people might get confused about is that why a single force will be broken up into two different components. And well, it always happens because you have to remember that which direction the force is trying to turn this object. And also you can avoid doing this method by just working out the perpendicular distance between the weight and B, but it's going to be the same method, but just harder to think conceptually. Let's go to question 6. So we have a small ball B is projected with speed u at an angle of theta above the horizontal from a point O. At time 2 seconds after the instant of projection, B strikes a smooth wall which slopes at 60 degrees to the horizontal. The speed of B is 18 meters per second, and its direction of motion is perpendicular to the wall at the instant of impact. B bounces off the wall with speed v meters per second in a direction perpendicular to the wall. At time 0.8 seconds after B bounces off the wall, B strikes the wall again at the lower point A. So find u and theta. With this kind of projectile questions, it's always helpful to think about the horizontal velocity first, because there's no horizontal forces in projectile motion. The only forces acting here is gravity, and it's acting vertically. So the horizontal velocity, which is u cos theta, will remain unchanged. And it should be equal to 18 this angle here should be 30, which you can convince yourself by some really simple geometry. So if we extend this line here, this will be 30, this will be 60, and this will be 30 again. This will be 60 again. So let me just erase this. The 18 cos 30 degree. And we also have a condition on vertical velocity, and so this is the condition on horizontal velocity, this is the condition on vertical velocity. And we get this condition by the definition of acceleration, because the gravitational acceleration is g, and it has taken 2 seconds for the ball to hit the wall. So the final velocity must be the initial velocity minus the amount it has been accelerated by. And if we square both sides, first move the 2g to the right, we get u squared is equal to 15.588 squared plus 11 squared. And that will give you u is equal to 19.1. And theta is in turn 35.2. And now, by considering the motion of B after it bounces off the wall, calculate V. So V is the velocity of the ball when it bounces off the wall. And to solve this question, let's think about the total horizontal and vertical displacement after the ball has bounced off the wall. And after bouncing off the wall, let's say the ball traveled a total horizontal distance of 0.8 v cos 30 degree, which is also done by noticing that when the ball is bouncing back, this angle must be 30 degree. And the total vertical distance traveled by the ball should be minus 0.8 v sine 30 degree plus g 0.8 squared over 2, which is a Suvat formula. And also you can notice the fact that because this angle is 30 degree, so 0.8 v cos 30, the x displacement, over 3.2 minus 0.4 v, the y displacement, must be equal to the tangent of 30, which you can see by geometry, and that will give you v is equal to 2. So when you're doing projectile motion questions, it's always crucial to think about the geometry of the setup and always resolve the velocity into horizontal and vertical components. And remember that the only forces acting is in the vertical direction, and you can use either the definition of acceleration or some Suvat formula to help you determine the change in vertical velocity. And the horizontal velocity is almost always unchanged unless it's going through a collision. 7, the last question of the paper. So a force of magnitude 0.4 n applied at an angle of 30 degrees above the horizontal acts on a particle P. Uh, 0.4 t, where t in seconds is the time since the force starts to act. P is at rest on rough horizontal ground when t is equal to 0. The mass of P is 0.2 kilogram, and the coefficient of friction between P and the ground is mu. And given that P is about to slip when t is equal to 2, find mu and the value of t for the instant when P loses contact with the ground. Okay, so when t is equal to 2, the contact force between P and the ground, so the normal reaction, is equal to the weight of the particle, which is 0.2 g, minus the vertical component of the force, which is 0.4 times 2 times sine theta, where theta is equal to 30. And the friction force will be equal to 0.4 times 2 times cos 30, because it's at the friction limit. So the pulling force will be exactly equal to the friction force. And now we have the reaction and the friction. We can determine the coefficient of friction by the formula that wait, it's the other way around, sorry. Because the friction will be equal to mu times R. So mu should be R over F, that's right. Wait, is it F over? Oh yeah, sorry. F over R. And that will give you 0.433. And when the instant when P loses contact with the ground is basically when the vertical pulling force is equal to the weight of the particle. So we just set up the formula that 0.2 g, the weight of the particle, is equal to 0.4 t sine theta, the vertical pulling force, and we get t is equal to 10 seconds. So when P is moving on the ground, it has velocity v meter per second at time t second. Show that dv by dt is equal to this thing here. And what's dv by dt? It's basically acceleration. So we can use Newton's second law to find the equation of motion. So ma is equal to f. So 0.2 times dv by dt should be equal to 0.4 t cos 30, which is the horizontal pulling force, minus 0.433, the coefficient of friction, times the normal reaction force, which is 0.2 g, minus 0.4 t sine theta. And simplify this equation, you will get the required equation of motion. And calculate the speed of P when you lose its contact with the ground. So now we have a differential equation for V and T, and it's trivial to integrate this equation up. So let's integrate this equation. So V is equal to 2.165 over 2t squared minus 4.330t plus a constant of integration c. And we know that when v is equal to 0, t is equal to 2, and that gives us the condition that c is equal to 4.33. And also from this we know that v is equal to 2.165 times 10 squared over 2 minus 4.33 times 10 plus 4.33, and that will give you v is equal to 69.3. And you can easily see that this can be used as a model to describe how airplane take off, and that's just quite an interesting point. Let's finish here.